Shalini Chandran. I'm from BERR Computer Engineering student. So today I would like to present my final year project, which is feature extraction of firing pin impression for the purpose of pistol recognition. So I'm going to introduce my project. So each pistol produces firing pin marks due to the interaction between the firing pin and the cartridge premium. So this mask can be analyzed to determine which pistol fired the bullet. So however, the manual examination of firing pin impressions can be difficult, subjective, and time consuming. So to address this limitation, an automated and systematic approach is proposed. So this project applies image processing and machine learning techniques to analyze firing pin impression images automatically. So the system first pre-processes and images and extracts important patterns from the firing pin impression. So machine learning models are then trained to learn these patterns and classify the pistol that produce the firing pin marks. So based on the background, there's several problem statements were identified. The main problem is that current system do not use enough image details. So because of this, firing pin marks from similar pistols look almost the same to the system. So when pistols are from the same model, their firing pin marks looks almost the same. So because of this, the system find it difficult to decide which pistol made the mark. So the differences between these marks are very small, so they are hard to detect. So therefore, a better automate method system that can look at more image details and classify pistols more accurately. So to address this problem, the objective of the project are defined. The first objective is to perform image preprocessing and segmentation, and the second objective is to extract statistical feature and fractal dimension by using differential box counting method. And the third objective is to classify pistol recognition in different pistols from the same model. So this project processes firing pin images, extracts features, and classify pistols of the same model. To address the adjectives, their methodology is proposed. So first, the firing pin images are collected as the dataset. So next, the images are pre-processed to improve quality. Then the firing pin are separated from the background. After that, the features are extracted and combined. So the dataset is split into training and testing data. So the machine learning is used to classify the pistols. So finally, the system performance is evaluated using accuracy and confusion metrics. So these are the project workflow. So the dataset used in this project consists of firing pin images from 5 pistols of the same model. So for each pistol, 150 firing pin images are used. This gives a total of 750 images for training and testing the system. So before the system can analyze this image, it must be cleaned and prepared. So because the raw images often contain noise and uneven lighting, so an unnecessary color information which may reduce the performance of machine learning models. So I have done the grayscale conversion, which means it makes the texture pattern clearer. So I remove the color and convert it to grayscale. So which means black and white. So along with noise reduction applied, which means cleaned the image where the image contains some dirt, so known as the black dots. So more to like get the image quality. So next, the image segmentation, where the canny edge method applied to mark the outline of the firing pin. So this method applied because draw the outline of the firing pin impression. So the system focuses only on the firing pin region. So where the unwanted background does not affect the analysis. So for the feature extraction, I've done choosing two feature extraction, which is the physical features and fractal features. So these features describe the image in numerical form so the machine learning can understand it. So the statistical feature describe the overall values of the image, such as brightness and variation. So this project uses 13 statistical features method. So for the fractal feature, measures the complexity of the firing pin patterns. So the reason I chose these features to my project are effective and suitable for implement similar firing pin impressions. So for the data set split into training and testing data. So the 70% of the data is training and 30% for the testing. The training data is used to train the machine learning model, while the testing data is used to evaluate the performance of the system. So in this project, there are three machine learning models were introduced, which is decision tree, SVM, and KNN. So the decision tree is a rule-based method that classifies data by learning simple decision rules from the features. The support vector machine is separates the different pistol by finding the best line between them, which make it suitable for complex and high dimensional features. For the K nearest neighbors class, which is the KNN, it classifies a firing pin impression by comparing it with the most similar samples based on the distance. So these models were chosen because they are commonly used in image classification and suitable for statistical and fractal features and allow the performance comparison and also require moderate dataset sizes. So by using these three models, the classification performance able to evaluate and compare to determine the most effective technique for pistol identification. So for the analysis of the machine learning techniques, first I test the decision tree models. To define tree model achieve an accuracy of 89.9%, which can classify most pistol correctly. However, such as the medium tree and coarse tree, the accuracy drops to 74.4% and 61.70%. This means simpler trees cannot capture enough details from the firing pin features. So next, I test the several SVM models. The linear SVM achieves 76%, while the quadratic SVM improved to 87%. So more complex SVM such as the cubic SVM and fine Gaussian SVM achieve very high accuracy up to 97 to 100%. So there are several KNN models with test. For KNN models, the accuracy depends on the number of neighbors and distance calculations. So the fine KNN and weighted KNN achieve 100% accuracy, while the medium and coarse KNN showed a lower accuracy between 60 to 75%. That means the KNN can perform very well, but it's sensitive to noise and might overfit when the dataset contains very similar samples. So this shows that SVM models are very effective in separating similar firing pin patterns, especially when the imaginary line is more flexible. So even though some models show 100% accuracy, I did not choose them because the 100% accuracy does not always mean the model is really good. So in my project, all pistols are from the same model and their firing pin marks looks very similar. So because of this, some models can overfit, so meaning they perform perfectly on known data but might fail on new data. Where the result part of the confusion matrix, the confusion matrix table shows how many images were classified correctly and how many images were classified wrongly, and which pistol was confused with which other pistol. So based on the confusion matrix, the dark blue boxes is diagonal, which is correct classification, and the light pitch boxes is off diagonal, which is a wrong classification. So where the horizontal axis is true class and the vertical axis is predicted class. So For the model 1, which is the fine G, what we can see the most values are on diagonal, which is good. The fine G model can classify most firing pin images correctly. However, the because the pistols are very similar, some images are confused with other pistols. So for the model 2, the SBM. So what we see, very strong dark blue, which is almost all pistols are classified correctly in very few mistakes. So the cubic SVM shows the best performance. So most firing pin images are correctly classified with very minimal confusion between pistols. So for the model 3, which is KNN, so what we can see, more of diagonal values, which is most of the wrong classification. It is because the KNN depends on the distance and sensitive to overlapping data. The medium KNN shows a more confusion because the similar pistols have similar features, so making it harder for distance-based classification. The confusion matrix clearly shows how well each model identifying firing pin impressions from the pistols of the same model, with quadratic SVM achieving the most reliable and accurate classification. So finally, this project supports SDG system, peace, justice, and strong institution by contributing to more reliable forensic analysis through automated firing pin impression recognition, which can assist law enforcement in firearm related investigation. It also aligns with SDG 9 Industry Innovation in Infrastructure by applying image processing and machine learning techniques to develop an innovative and systematic firearm identification approach. In addition, the project supports SDG 4, which is quality education, by enhancing technical knowledge and research skills in forensic engineering, image preprocessing, and machine learning through practical project based learning. So, last but not least, among all the test machine learning models, SVM, the support vector machine, which is SVM, is the best performing model. So the SVM achieved the highest and the most consistent accuracy during validation and testing. So unlike KNN, which showed unstable in some cases, and decision tree, which had lower accuracy. So the SVM was able to separate the firing pin impression patterns more effectively. So this SVM is the most reliable model for firing pin impression based pistol recognition in this project. Thank you.